Hey, 4U Physics. How are you guys? I wanted to start Unit 4 with you. Just do some of the highlights of what that unit is, which is energy. And what we'll do today is we'll start with the sections 4.1 and 4.2 in the textbook. So the first thing I wanted to talk about was the idea of work. What is work? It's not the job you go to. It actually has a physics definition. The definition of work is the energy that a force gives to an object over some distance. And it's kind of important to look at not just force. We've been looking at force in Unit 3 and in Unit 2. And, you know, the math is nice. It's nice and clean. But the problem with force is realistically, when you start looking at forces in real life, they're all over the place. So when we have forces in this class, they're always just mass times acceleration, and acceleration is constant. And so our force is this nice constant thing. And it's easy to do all the math, but in real life, force is typically a function of time, and it's usually some graph that's all over the place, right? Especially if it's a human applying it. You can't apply a constant force even if you try. You know, when you first start pushing something, you add a lot of force, and then you let off the force, and so force isn't really a good thing to always look at in physics questions. And the math is easier if we actually look at energy instead of force. And so we're going to do that. So this function, or this new unit, or new entity, excuse me, is called work, and it's just defined as the force vector dot the distance vector that the object travels. So the force on the object the whole time dot the distance it travels. And in calculus, hopefully you see that the dot product is basically the force vector projected onto the direction of the distance. Or it's actually F times D times the cos of theta, the angle they make between each other, right? If force is over here and distance vector is over here, oopsie, we're actually looking for kind of, where's that little green? That green. We're actually looking for like the projection of this vector onto the distance vector, right? Like that. We're basically collapsing this component of the vector. Basically, it's x component if d were our axis. Okay. What are the units of work? Where's my pen? Can never find it. Oh, there it is. The units of work are newtons times meters, and that has its own definition, which is called J, which stands for joules, named after one of those guys. This might have been the steam engine guy, I'm not sure. So if we take our force, we times it by our distance, and obviously the cosine that they make between each other, or the force vector dot the distance vector, we get a new unit called joules, which is energy. Okay? Joules is what we define as a term called energy in physics. So that's all well and good. Can we think of some really basic examples? Sure. Let's do that. Example number 1. I'm just going to make these up from the top of my head. A 11 Newton force is applied. I'm going to go to the book's way of doing things and take like some stupid object and put the force on that. Is applied on a toboggan. Toboggan. I don't even know how to spell toboggan. I think it's 2 G's. You could fix that in your own notes. An 11 Newton force is applied on a toboggan over a distance of 13 meters. The force is applied at 40 degrees to the direction of motion. The initial questions are very easy, right? What work was done? That's how you phrase it. What that work is done on something. What work was done on the toboggan? Okay. So it's one of these kind of fill in the blanks where you have your work. Work is a scalar, by the way, because a dot product is a scalar. And so is energy. It doesn't matter what direction you apply things in. Energy is not a vector. It's just a value. It also makes the math easier later on when we do some crazy kinematics questions. Instead of using force and acceleration and time, if we just use energy, we don't have to worry about vectors at all. It makes our life a little bit easier. So what's our force? Our force times our distance times the cosine of our angle. Force was 11 newtons, distance is 13. Yeah, you get the idea. There you go. Fill in the answer there. Okay, so that's a really basic example. Could we have negative work? Yes, we could, right? Let me see what an example like that looks like. Example 2. The toboggan. So let me just work out this answer before we go on to this, because I want to still use the same toboggan. All right, so this answer is 110 joules, okay? Which means, and it's positive, which means somebody put some energy into that toboggan to get it moving, okay? The toboggan is moving too fast, okay? A brake, some of these things have brakes on them. A brake is applied with a force of, let's say, I don't know, 500 newtons over a distance of 3 meters in the opposite, you have to be explicit about this, in the opposite direction of travel. Okay. The question asks, how much work is done on the toboggan? So this thing is moving now, right? Here's the toboggan, and its distance is this way as a vector, but the force is the opposite, like that. Okay, so If I want to find the work in this case, I just I use a cosine of 180 degrees because they're 180 degrees apart from one another in direction. So I'll do F times D times cos of 180 degrees. And my force is 500, and my distance is 3 meters, and the cos of 180 degrees is -1. So the answer is 1500 joules, and it's negative. So that means energy was taken away from this toboggan. Okay, positive energy here means you're adding energy to the toboggan to make it move. And when you get negative work, you're taking energy away from the thing. You're trying to slow it down. Hopefully that makes sense. You can also have zero. Let's do a really basic example where you get zero work. This is a silly example, but example 3. I don't know. A crane pulls up on a airplane with a force of 10,000 newtons. Just making all these numbers up. The plane only moves, this is a really bad example, horizontally. Maybe it's moving a little bit with the wind or something. 10 meters, right? What work does the crane apply to the plane? So if you think of work as like adding speed or taking away speed, does the crane add or take away from the speed of the plane? No, it doesn't. It's pulling up on the plane. The plane is only moving horizontally. So if we look at this picture here, I'm going to draw a box. I'm not going to try to draw an airplane or a crane. The crane is pushing up like that, right? And the plane is moving this way. So the angle between those two forces is theta, or theta is 90 degrees, and the cosine of 90 degrees is 0. So work is equal to 10,000 times the distance times 0, which is equal to 0. So the crane is actually not giving the plane any energy. Okay, so you can get examples where, I mean, I don't know, I think it's kind of a contrived question, but you can get questions where the force and the distance are perpendicular to one another, and then no energy is given. Hopefully that makes a little bit of sense. So the other thing we want to look at is how this work relates to some of the stuff we've been doing. So here is our formula for work, right? And we do have some formulas that have distance and force in them, acceleration and stuff. So let's look at those. We'll do that just with, we'll consider an object. We'll just get some basic formulas for today. Consider an object of mass m. I'm not going to put any numbers in there yet. Accelerating horizontally across maybe like a tabletop or something. A distance d. Okay. So there's my hockey puck or whatever, and it's accelerating that way, and it's going to move a distance d, whatever the length of the table is, it's going to move a distance d. Okay, so my equation for whatever, something has to be accelerating it, right? And so something has to be putting energy into it. So there is work being done on that hockey puck. For us, the dot product of F dot D, the force is in the same direction as the acceleration, which is in the same direction as the distance. So in this case, the work is just force times distance. Most of the time it will be like that. So work is equal to F times D. F is just equal to MA, right? MAD. Work equals MAD. And I'll just write, since F is equal to MA, right? So I'll replace the F with MA. I have an equation with AD in it. Maybe you guys remember this, maybe you don't. We didn't use it that often, but this was the equation for the just erase that there. It is going to be VF squared equals VI squared plus 2AD, something like that. That's the equation there. And that was equation 4, I believe. So I'm going to take that and rearrange it for AD. So I will say that 2AD equals VF squared so I got 2AD equals VF squared minus VI squared. Okay, that's the one that doesn't have any vectors in it. Remember, I didn't like using this formula that often because it doesn't use vectors because we're squaring stuff. But it's good here. We don't have any vectors really. Like, we're in a 1D situation. It's totally fine. And so AD here is equal to VF squared over 2 minus VI squared over 2. I just brought the 2 here underneath both terms. And so therefore, my work formula MAD is now equal to M, but now the AD I'm going to replace with VF squared over 2 minus VI squared over 2. Okay? And so I get this nice formula here, and I'm going to rearrange it a little bit more. One half MVF squared minus 1/2 MVI squared. So the work done on an object is equal to 1/2 times the mass times velocity final squared minus 1/2 times the mass times the velocity initial squared. And here's something that we haven't talked about, but I think you see in grade 11 for sure. This 1/2 MV squared thing, right? If we call 1/2 MV squared the kinetic energy, right? And we call it kinetic energy because it has a velocity term in it, and kinetic means moving. And so it's the energy of an object that's moving. We're looking at the energy that an object has when it's moving. If we call 1/2 MV squared the kinetic energy of an object, yes, then we can redefine work as this. It's equal to the change in the kinetic energy, right? Because it's equal to the kinetic energy. We call the kinetic energy, by the way, EK, like E, big E with a little subscript. So this term here right? It's just the kinetic energy of the final velocity, and this term here is just the kinetic energy of the initial velocity. So EKF minus EKI, like that, is just a change in kinetic energy from the initial to the final term. Okay, so this formula here is what all this work was for. It's saying that the work, which is equal to the force dot the distance, is also equal to the change in the kinetic energy. So we're relating, what we were trying to do is basically relate all of our new energy term stuff into our kinematics unit. And our kinematics unit just used force, mass, acceleration, distance, and time, right? We haven't seen time pop up yet here, but this is all kinematic stuff, and then that's going to equal the change in kinetic energy, which is 1/2 mv squared. There's no vectors in any of this stuff, so the math is actually going to be a lot easier. So that's an important formula to look at. Okay. If we wanted to, I don't know how far you guys have gotten in calculus, but there's some cool calculus formulas for this stuff as well. If, for instance, the force is not constant and the distance is changing and all of that stuff. Okay. Let's just look at one example today, and then I'll maybe throw some examples for you to try on the Google Classroom. So, example 1, a whale. I think I must have taken this from the book. A whale of mass. The questions are so silly to start with, especially, right? They don't want to make them too complicated, so they have to take these funny objects and pretend like they're measuring them. A whale of mass 1.5 times 10 to the 5 kilograms swims with a speed of 6.1 meters per second. Okay, so that's its kind of starting speed. It increases its speed. I'm going to erase that. Wish me luck on this. Oh, it worked. It increases its speed to 12.8 meters per second. Calculate the work done by the whale. He obviously had to paddle to get going faster. Calculate the work done by the whale. So the whale did work on himself, right? Work is equal to joules. Another unit for energy is calories. So you can see that, when you're doing work, you're burning calories, you're using up your body's energy, right? To make yourself increase in speed, or to actually, when you're giving work to other objects, you're burning that energy, right? You're losing the energy and you're giving it to, the treadmill or the dumbbells or whatever you're doing. And so you're burning energy, and your body typically uses, like fat to get that energy, or your muscles or whatever. So, that's how you can get fit at the gym. Okay, so let's calculate this. The work done is just going to be the change in the kinetic energy. The change in the kinetic energy is just going to be 1/2 times the mass times the whale times its final speed, which is 12.8. That has to be squared, because that is 1/2 mv squared, and then that will be subtract 1/2 m times the initial speed, and that's the work that the whale did in joules to get up to that speed. What is that answer? Let's look. I'm going to use my calculator here. And I'm going to subtract 0.5 times 1.5 times 10 to the 5 times 6.1 squared. They're fairly big numbers just because you're squaring all the speeds, and the whale's got a really big mass as well. So the work done is 9 million joules, or 9.5 million joules, something like that. This is the number I get. Okay. So that is the work done on the whale to get him going faster. Really basic for now. We're going to look at, though, some more properties of energy later, and conservation of energy and potential energy, and how they all relate to each other, how they can make our questions easier. So I'll post this video on the Google Classroom, and you can also, I'll put some questions for you to try as well on there. Okay? Talk to you soon.